In my previous video I estimated the analytical theta for a butterfly, and that took the shape. So we had we estimated the each of the individual thetas for the option positions, and then worked out the value of the portfolio and regenerated the butterfly theta for a variety of different stock prices going from 10 to 200, where the underlying was a stock or could be considered to be a stock. In this next video I'm going to I'm going to estimate a computational or numerical theta, and that also will offer us some insights in how to interpret what theta represents and how we might apply it to a butterfly portfolio of options. So we'll say computational theta, and we'll set out the value of the butterfly. So we'll just copy and paste, and it looks as if the values here are still live. The formula are all referring back and seem to be working. So to remind ourselves what theta represents, it is a measure of time decay. And so what we would like to observe is the effect of the value on the portfolio with respect to change in the time period. So again, we could recalculate the portfolio, and again we have the same result, and then we could consider in this instance both volatilities were just a little bit different. We could change that to 20% and then consider a time period or maturity on the contract equal to, let's say, 1 year, and put 1 year below. And we could look at the effect of reducing the time period, or initially we could add a very small increment to the time period, so 0.0001, so that's a very small increment, where 1 represents a year and 0.0001 is in terms of annual units or years. And likewise beneath we could say subtract equal to 1 minus 0.0001. So we're looking at, broadly we're getting the same result here, but tiny differences do exist between values. So if you drill down a small amount, you'll see that there are variations in terms of valuation. And also we have the portfolio here is made up of 2 long call options and 2 short call options. To replicate the value to estimate the computational theta, we could set up a data table as we had done before and considered a range of different time periods. So we could consider going from, as here, 10 to 200. So 10, 20, highlight and pull and drag. And we could set out the time period, the portfolio value at the higher time period. the portfolio value at the lower time period. This is less than a year, this one was higher than a year. And then we could run both time periods. So let's take this again. Cut. And we'll paste here. And run this again. Okay, so to run the data table, data tab, what if analysis, data table, and column. And I need to make one additional change here. This cell should be equal to the cell above, so that when we change 100 here, it's also changing here. So I'll have to rerun that table again. In fact, it's updated, but let's just rerun again. Data, tab, what if analysis, data table, column, and then in the original parameter input that I want to change is the stock price. Okay, and we get the same anyway. Okay, so recall that this relates to the higher time period. So T equal to 1.0001. So we should use, in fact, uppercase T, and also T equal to 0.999, just to be consistent with the value we have here and the value we designate here. And then we put those values in as the time periods involved. So we'll say 1 point, or in fact we could say equal to this time period and equal to the lower time period. Okay, and then pull both of these down. F4 and pull down. And again, I should have locked the cell reference. F4, hit F4, dollarize the cell reference, and it locks. And pull it down. Okay, so to estimate theta, to estimate this variable, in order to look at time decay, we must take we must consider the effect of changing the time period and the value of the option, or the value of the option portfolio. So very simply, we would say the longer the portfolio value with the longer time period minus the portfolio value with the lower maturity, and then because it's lowercase t, we reverse the order and we use the lowercase value, the lower maturity value minus the higher maturity value, and that's the capture time decay. Okay, and then we pull it down, and we could, well, in fact what we could do is go back to our analytical theta and change the value to be 0.2, just so that it is equivalent to what we have, and to 1 year. And then take this value range for the analytical theta and compare against the computational theta. And I should paste special values. Okay, so let's have a look. And there is a small difference, yet again, but not substantial. It tends to be quite small. So if we compare these two values, we see that the analytical theta is equivalent to the computational theta, or numerical theta. Maybe I should use numerical. In other words, the theta we derive from Black-Scholes model is the same as the theta we estimate by taking this ratio of the value of the option, or the value of the option portfolio with respect, changing the value of the option portfolio with respect to changing the time decay, where lowercase t denotes the time passed. And in this instance, the time passed is 0.0001 of a year. Okay, let's just graph. So we'll insert graph. And let's undo that. So insert, scatter, and we will select data and remove, and then add, and say numerical theta. And on the x-axis we'll take the range of asset prices, and on the y-axis we take the numerical theta. And if we compare, so hit OK. If we copy, maybe we'll look a little bit at the design here. And copy. Let's improve this a little bit. We might say on the horizontal axis we had the asset price, and on the vertical axis we have the butterfly, or butterfly theta, and it's numerical. And we can copy this, put it into the previous worksheet, and just make the comparison. And we can see we're getting the same graph. Okay, so the numerical theta is equivalent to the analytical theta. Okay, and this also, again, by looking at the numerical computation, it's quite clear what theta represents. Theta represents what is the effect of a small time period passing. And if we're at the, as in this instance here, when we're at 100, what we can note, it's possible to observe that when we're at 100, a reduction in time leads to an increase in the value of the butterfly portfolio. A reduction in time leads to an increase in the value of the portfolio when we are midway between the two, the upper and the lower and upper exercise. So when the asset price is at the middle exercise, then an increase, a reduction in maturity, or an increase in amount of time that's passed since the option has been set up, leads to an increase in the value. When we move out at a range close to the middle exercise, this can become negative. But close to the exercise, we find that a reduction in the maturity of the contract, or a reduction in the outstanding remaining time left to maturity or expiry, leads to an increase in the value of the butterfly option portfolio.